Okay, here we go with the atomic orbitals and electron configuration. I'm going to show you the presenter view so that I can write on the slides. So we're going to talk about atomic orbitals and electron configuration, and the vitaliest, the most important or vital rule of all of chemistry is Coulomb's law, and that is that opposite charges attract and like charges repel. And that force is stronger the closer they are, and it is stronger with higher charges. So this illustration is showing you the relationship between particles that have the same charge. And so as you go closer to the nucleus, particles that are, or as the particles get closer to each other, as the potential energy increases as they are getting closer together because they are becoming less stable. And like charged particles are more stable when they're farther away. If you have if you had like charged particles, it would look like this, right? Where you have particles that are farther away from each other, less stable than the ones that are closer to each other, because this is a lower potential energy, is a more stable system. And then here is just a basic illustration of the attractive forces and repulsive forces within an atom. So if you have an electron, it is attracted to the nucleus, right? The electron wants to be pulled into the nucleus, and the nucleus wants to pull the electron closer to it. Whereas if you have electrons, they are repelled by each other, and the protons are repelled by each other. So opposite charged particles attract, and like charged particles repel. And so when you're adding more electrons to an atom, to an element, those electrons have to go into additional orbitals that are farther away from the nucleus. This is a beautiful illustration down here that shows you the difference between a 1s orbital and a 2s orbital, right? There's a 1s orbital here where the electrons are very close to the nucleus, right? And then you have the second energy level where they're farther away from the nucleus. But notice this node in here, this node part right there, there is no electron density there, right? The electrons have to be promoted by adding energy to them to hop from the 1s orbital to the 2s orbital where they're farther away from the nucleus. And this is because of Coulomb's law, right? As electrons get farther away from the nucleus, they are higher in energy because they are farther away from that attractive force. So this gives us the shapes of the different types of orbitals. We have the s orbitals here, the spherical orbitals, the simplest orbitals. And then you have your p orbitals down here, right? The px, py, and the pz, depending upon how you're orienting your axes, right? There's three completely equal in energy orbitals on the p-axis, or on the p level, with the x, y, and z axis. Then you have your d orbitals down here. We have our d orbitals here, right? Where you have 5 different degenerate d orbitals that are like double propellers, right? And then down here you have your beautiful f orbitals that look like flowers. And so this is the basis of what you've probably learned so far about electron filling order, right? You do fill the S first, and then the P, and then the D, and then the F, because S is lowest in energy, then P is next highest, and then D, and then F. But sometimes it's not that simple, and so you set up your illustration of the orbitals, and you draw diagonal lines through it, and you have your electron filling order, right? But what evidence do we have that elements live in these types of orbitals? Well, that comes from photoelectron spectroscopy. And in photoelectron spectroscopy, you are adding energy to an atom and ejecting electrons, and then you're measuring the energy that those electrons have. And so this tells you the relative number of electrons on the y-axis, and then your energy on the x-axis. And so how does this work? Well, if you've taken AP chemistry, you've probably talked about this, but if you haven't, let me give you a little really brief rundown of how this works. So in photoelectron spectroscopy, you have light coming in, and I have this light purple because it's usually high ultraviolet light, possibly X-rays, that are shined on the atom, and then the electron absorbs that energy and then is ejected. And the kinetic energy of the electron is measured, and because the kinetic energy of the electron is able to be measured, and you know the intensity of the light or the wavelength of the light that you shown on that element, you can determine the binding energy that that electron has, because the amount of energy that was absorbed by the electron is the same as the binding energy that the electron had that was keeping it close to the nucleus. And so then what you get is you get a spectrum that is a little bit backwards, because the 0 is on the right-hand side as opposed to the left-hand side, right? But it shows you over here where the electrons are that are most tightly bound to the nucleus, because they have the highest energy, right? And according to Coulomb's law, the electrons that are closest to the nucleus will have the most potential and the lowest potential energy, and so they will be the most stable, the most tightly bound to the nucleus. And then you have electrons that are farther away, the valence electrons on the outside will be closer to 0. They'll be closer to the lowest amount of binding energy. They are the easiest to remove. This also shows you that our idea about S and P orbitals is correct, because you'll notice that this peak here is about 1/3 the height of the peak here in C. And so because A is 1/3 the height of C, and we know that there are 10 electrons in an element of neon, then we know that this represents the 1s 2 orbitals, and this is the 2s, and then this is the 2p. And that is validation that the electron configuration that we have figured out theoretically is matched by reality. And so if you look at the second row elements, we go from lithium all the way to neon. I wanted to draw the electron configurations for you. And so you have your 1s orbital at the bottom, and then your 2s orbital here, and then your 2p orbital here. And you want to notice that as lithium has atomic number of 3, right, and then neon has the atomic number of 10. And so there are more protons in the nucleus of neon than there are in lithium. And what that does is it attracts these energy levels more. So these, the 2s and the 2p electrons are drawn closer to the nucleus by the fact that there is a higher effective or higher nuclear charge. And so when we add electrons to them, lithium has 3 electrons, and so 2 electrons in the 1s, and then 1 in the 2s, and so on and so forth. But these electrons are getting closer to the nucleus as you get the effective as the nuclear charge is increasing. And then this brings us to the idea of effective nuclear charge. So remember that lithium has 3 protons, right? But the effective nuclear charge felt by these outside electrons is +1, because these 2 core electrons are canceling out effective nuclear charge. So these are like -2 all the way through, right? -2 all the way through. And so even though beryllium has 4 protons, the outermost electrons are only feeling a +2 effective nuclear charge, because these inner electrons are canceling out 2 of those charges. And so that is why you see this trend of the electrons getting closer to the nucleus, because there's a stronger pull, and electrons are more attracted to a higher effective nuclear charge. This helps to explain all of the periodic trends that we see, the periodic trends that you've probably learned about with atomic radius and how atomic radius decreases as you move to the right on the periodic table, how ionization energy increases as you move to the right, because as these are drawn down, these energy levels are closer to the nucleus, they have a lower potential energy. The amount of energy required to raise them up to this standard like ionization level, right? Let's just say that's your ionization level, right? You have to raise this electron less than you have to raise these electrons. So the ionization energy decreases as you go to the right because of this effective nuclear charge idea. And so what are the consequences of effective nuclear charge? Well, atoms with low effective nuclear charge form cations because they lose electrons. And so here's my cation. Notice he has positively charged ions. And then we have atoms with higher effective nuclear charge. They tend to gain electrons. And then they form negative ions called anions. And this is my beautiful little ion. Notice you don't usually pronounce the T when you're talking about anions, right? But the question becomes, what happens to atoms with medium effective nuclear charge? The ones with medium effective nuclear charge, like +4 or so, is right in the middle. That's where carbon and silicon are on your periodic table, and they tend to form covalent bonds, right, as opposed to ionic bonds. They don't lose electrons, they don't gain electrons, they tend to share their electrons, right? And that's because the effective nuclear charge is too low to attract the electrons enough to steal them from another atom, but it's also too high to give it away, right? And then what about transition metals? Well, transition metals all have an effective nuclear charge of essentially +2. And it varies as you go from left to right through the transition metals, but they're effectively +2. And we'll talk a little bit about why that is. And the intertransition metals are the same way, because the electrons that you're filling in the intertransition metals are the f orbitals. That's the lanthanide and actinide series. The f orbitals are even buried further down in the atom, and so that allows them to have a very interesting chemistry, very interesting electron chemistry, because of the fact that their electrons that are different from each other are shielded from the outside world because they're in an energy level too below where the valence electrons are. And so what you see happening with transition metals is that you have the Aufbau configuration just like this, right? 1s first, then 2s, then 2p, then 3s, then 3p, and then you learn that 4s and is filled before 3d, right? Because 4s comes before 3d in the filling order. But when you get a sample that's more than one atom, and then you start to try to remove electrons, you remove the 4s electrons before the 3d, right? The 4s electrons are the first ones to go. And so you find transition metals have most common charges of +2, right? Because they're removing those 4s electrons. And then the 3d become the outside or valence electrons. And that leads to some very interesting chemistry that happens with transition metals that we're hopefully going to explore in this course. And so now I want to move on to a topic that isn't actually about atomic orbitals. It's more about molecular orbitals. But since we're showing you energy levels and electrons, I think it still will fit. It still will work. So the idea is the HOMO-LUMO gap. So HOMO stands for highest occupied molecular orbital, and LUMO stands for lowest unoccupied molecular orbital. So I'm going to illustrate this with atomic orbitals that are not molecular orbitals by any means, but just to show you that the energy gap idea is the same. So there's an energy gap here, right, between the 3s and the 3p. So the 3s would be the highest occupied orbital, and then the 3p would be the lowest unoccupied orbital. And if you add energy to the electrons, right, this is the electron with the highest energy, right? And then it would be the most easiest to ionize or to add energy to. Then that electron can be promoted up to a higher energy state, right? And then you get this kind of a situation where you have an electron in an excited state, right? And electrons that are in excited states have options. What they can do, they would like to release that energy and go back down to their normal ground state. But then you could also do stuff with them, right? You can make them react in this way. And so this leads me into the idea of spectroscopy, the interaction of light and matter. And so as energy increases, in this case going to the left, you have gamma rays with the highest amount of energy, right? And then X-rays, then you have ultraviolet rays, and then you have your visible spectrum right down here, the light that we can see. Then the infrared light, lower energy than that. Then you have microwave radiation that is lower energy than infrared, and then you have radio waves as the longest wavelength or the lowest energy, right? And so what you do with this is you can look at that visible spectrum. And so this is for hydrogen. And when hydrogen absorbs energy, when the electrons absorb energy, you see that there are absences in the continuous spectrum for hydrogen because those wavelengths of light were absorbed by the hydrogen sample, right, by the atom, and the electrons were promoted to higher energy states. And then when they get that energy in the highest energy state, higher energy state, then they can emit that. And so you can look at it as what light was absorbed by that atom or what light was emitted by the atom when it's in an excited state. And so this is just a little intro into spectroscopy. We're going to be doing hopefully a lot of stuff with spectroscopy. So I wanted my first lecture for you to include a little bit about that. And so there you go.